So if we take out our highlighter, and the idea of an inverse is undoing the function, just like we saw here. G of x undoes f of x. Graphically, that shows up as a reflection in the line y equals x. If we would look at the first one, 2x plus 4, and we would graph the inverse, 1/2 x minus 2, we would notice that it has been perfectly flipped over the line y equals x. So they had this example that f of x is 2x plus 4. If I would take 2x plus 4, switch the x and the y, and now solve for y, I'd have to move the 4 over and divide everything by 2. And if I had x minus 4 over 2, I could write that instead as the x divided by 2, which is the same as a half, x minus 2. This is nice because it's in y equals mx plus b form, so you could graph it really easily. So if we go to our first example, they give us the graph of g of x, and so in blue, we want to graph the inverse. So two things we could do. We could do it graphically, where you have to flip it or reflect it over that line. Sometimes it's hard for our brains to flip over a diagonal line. Okay? On the exam, they will never notice you're cheating if you take your paper and turn it so your diagonal line is horizontal. It's really easy to flip over a horizontal line. It's not really cheating, but it helps your brain, right? If you turn it sideways, it's easier to flip. Okay? Algebraically, we have to switch x and y. That is probably the easiest thing to do. For example, this point right here is -4, 4. If I take my x and my y coordinates and flip them, I will get 4 for x now and -4 for y. All I've done is take my x and y and switch them. Same thing for this point. This point is 1, 3. If I switch them, I get 3 comma 1. If I did that for all 4 points, notice that this one, since the numbers are the same, when you switch them, they're still going to be the same. That should make sense. And for the last red point, right here, which is at 3 comma 2, on my blue graph, I get 2 comma 3. Now sometimes it can be a little tricky when joining the lines to make sure you join them correctly. Okay. This is where actually visualizing flipping it over will help you see. Another thing you should always do when reflecting a graph is wherever the diagonal line intersects, you should add that point, because that's where the x and the y are the same. And if you flip them, they're still going to be the same. So we've done part A. And a little reminder from grade 10. You can tell something's a function by using the vertical line test. There's the vertical line. There's the vertical line. If I go across, do I ever hit the blue graph more than once? Yes, right there. Doesn't matter. It just has to happen at one place that you hit it more than once. So the blue, okay, is not a function. What about the original one? The red graph. If I move through the red graph, can you see that no matter where I go, it only hit it once? Domain and range. My original graph, smallest x value is -4, biggest x value is 3. So in integral notation, it goes from -4 to 3. And for my range, my smallest y value is -1. My biggest y value is 4. Now if we look at the graph, the new domain of my blue graph goes from -1 to 4. And my new range goes from -4 to 3. And if it's an inverse, if the whole idea of an inverse algebraically is your x's and y's get switched, it shows up in your domain. Notice how there's just a switch. The range became the domain. The domain became the range. So sometimes on the exam, they're gonna ask you a specific detail like that. They're gonna say, the domain of f of x is -4 to 3. What is the range of f inverse? And then you'd have to know that they would be the same because they switch. All right, please circle questions 4 and 9.